Welcome to the last session of our first day of Climate. This session, we will be hearing from Robin Troesch. Robin is a data engineer for electricity maps, as previously worked as a software engineer on security at Microsoft. So electricity maps is leading API for granular electricity data with a goal to reduce carbon emissions with actionable electricity data, providing that data for more than 160 regions. Electricity Maps helps businesses reduce their emissions and empower end users to be more carbon aware. Robin holds a Master of Science in Computer Science and Engineering from the Technical University of Denmark, and his current focus is on climate awareness and decarbonization of the electrical grid. Robin will be talking to us today about predicting the best hour to run heavy computations with a minimal carbon footprint. And I feel this is a particularly relevant way to finish our sessions for today, because we've heard about all of the different ways that we want to be doing those heavy computations. So when should we be doing them? So thank you so much. And please join me in welcoming Robin to the stage. Robin, if you want to go ahead and come on and join. And share your screen. The stage is yours.
Thanks. Just a second. All right. I think this works.
Yes.
Great. Well, thanks for the introduction. Super happy to be here to talk a bit about carbon-aware computing and how we can schedule our workloads accordingly. So a little bit about myself, but most has been already said. As I said earlier, I'm Robin. I'm a French data engineer working here at Electricity Maps, based in Copenhagen. Living here and having an education in computer science. And like almost everyone here, I bike every day to work. But besides bicycle, we have a nice agenda for this session. There's a lot of unravel before we can talk about scheduling your computations. We're going to start with a quick intro into electricity data, talking about what is load shifting, before diving into the inner workings of our ML setup. So let's kick off with a few words about what Electricity Maps does and who we are. So Electricity Maps was founded a few years ago with the desire to help the decarbonization of the electricity grid. We gave ourselves the mission to organize the world's electricity data to drive the green transition. We started with an open source app to display the origin of electricity in real time, and it's powered by our amazing community. The app is both used by experts and enthusiasts to learn about the electricity grid and the origin of your electricity. And with that said, I'm going to quickly show you the app because it's way more visual than long sentences. So this is our web app, for instance. It's also available on your mobile devices. And if you, for example, click on the zone, let's take here the New York zone, you can see its carbon intensity in real time, its share of low carbon factors, renewables. Also, you can see the share of each production mode, how much it's used. You can also see how much it imports in real time from neighboring zones. So for example, here from Canada, the two Canadian zones, how much it exports, the carbon intensity in this zone over the last 24 hours, where the electricity comes from also. So that is mainly us, but there's actually a bit more. Besides our app, we are also providing an API which allows our customers to access unified hourly electricity data. We can provide historical data used for mainly carbon accounting purposes, also research on policy impacts. And the nice part about this is that parts of this historical data set is available freely for anyone through our data portal. So if you ever want to work with electricity data, check it out. It's quite nice. We then have our real-time data offering, which customers use in their user interface to display, for instance, the carbon footprint using their product. And finally, the last part, our forecast, which is what we are going to focus on today. And we are right now offering a 24-hour look ahead forecast into what your grid state will be in the next hours. So before we dive into this, maybe a little course about electricity data. What are we talking here about? So I already showed you the app a bit earlier, and maybe you noticed there were two sides of the story, consumption and production. And I'm going to try to answer the question about what is your consumed electricity. So in order to consume electricity, you need to connect yourself to a grid. For each grid, there's a grid operator responsible for balancing electricity producers and electricity consumers. In the US, those are called usually balancing authorities. In Europe, we call them transmission system operators, TSO for short. And to fulfill their mission, the grid operator is coordinating electricity producers and handling imports and exports of electricity with neighboring grids. It might be cheaper for them to import cheap wind energy produced by your neighboring grid rather than producing a expensive gas-powered electricity. So this means that the grid mix, which is the energy sources used to generate electricity on your grid, are not always the same as all the producers that are available on your grid. All the grids are interconnected, and therefore to establish the electricity mix of your grid at a given time, you need to take into account imports from other grids. There is way more to this, but for now, I think this will be way more than enough for what we're going to talk about in our session. So now let's actually talk about how we can avoid carbon emissions. So as I said, your grid mix is actually never really static. It fluctuates throughout the day. Even more nowadays with the extensive integration of renewable energy in the grid. This is, for example, the hourly share of renewable energy available on the British grid in September. If you're aiming to reduce your carbon impact, you should schedule your electricity consumption to make sure that you maximize the number of hours where your consumption will be supplied by low carbon energy sources. Typically here, if you wanted to train a large language, for example, you should maybe leverage those days at the end of September where there's a lot of wind energy available. Or maybe if your model is very short to be trained, maybe you should just leverage one of the solar spikes that are here because they provide clean energy as well. You should also be aware that maybe here, if you just start training now, there is a spike in wind, but it's going to drop in a few hours. So if your model is trained for a long time, well, tough luck, you're going to use coal in the end at some point. And this is what Google, one of our partners, does with our data. They are trying to optimize their data centers' workload to maximize their low carbon electricity usage. The challenge here is to be able to make accurate enough forecasts about what will be the share of low carbon production modes so that the carbon intensity is the lowest at a given time, and kind of like predicting the grid state over the next hours or even days. And this is where our forecasting team comes in. So now I'm going to walk you through a bit how we are trying to solve this challenge and building our prediction engine. But before that, just a little word about how we are collecting this data to build our data set on which we're going to train our models. Well, we are collecting data from external sources like government agencies like the EIA in the US, and so we in Europe, regional load dispatch centers in India, the market operator in Australia, just to name a few. All those sources publish their data in about their production, consumption, and exchanges in their own format. And we have an amazing open source team that is writing parsers for those external data. They will convert the raw data into our event structure, where we can normalize all those inputs into our event database. Once they have been collected, we have a first pipeline making sure that the data is correct, eliminating outliers when we detect them, and also making sure that our data is complete. And if we have missing data, for example, we're going to try to estimate the gap to fill in, because honestly, electricity data can be complex sometimes and have a lot of gaps that you need to fill in. And finally, there's the flow tracing pipeline. This is where we're going to compute the origin of the electricity. As the name suggests, we are tracing back the flow of electricity, matching production exchanges with the consumed electricity for a zone, establishing its state. And this state data is then shown on the app. We are also collecting some weather data, but more about it later. So once we have this, the state database that is established, we have a historical data set that we can use to make predictions. Okay, so now I just went through how we get historical data and near real-time electricity data. But how do we look into the future? Well, let me take you through a journey to build a prediction engine. In our first iteration, we were sitting on this huge data set of historical data and thinking, okay, let's predict carbon intensity and the power breakdown of a grid. Initially, we wanted to keep it very simple to be able to focus more on the data collection, which was more priority at this time. And therefore, we developed this product kind of as a separate offering a bit, which will have consequences later along the way. So that's how we started, like typing into our historical data sets. Here, for example, for a single zone, like I think this is the New Mexico zone, if I remember correctly. Well, we had off a feature engine loading a chunk of data, around 3 to 6 months of the most recent historical data for this zone, and turning into features for our models. That's where we start using the weather data that we mentioned earlier. We have features such as the current wind speed, the forecasted wind speed over the next few hours, the consumption in the last days, the most recent production, the exchanges, the forecast exchanges, the price information. And we use this to train our models with actually simple models to begin with, just linear models. And knowing the carbon intensity of each zone, we were directly trying to use the linear lasso models to find the most relevant features and use them to directly predict carbon intensity. We did the same to get the power breakdown of each zone and stored all of those predictions into our special prediction database that we could then serve to customers. Quite simple, and it worked quite well enough for a while. We were training all of those models into a notebook and shipped the models along with a code base. So it was quite simple to roll out something. Every hour, our models were fed with the latest data that it was available, and the predictions would be made and stored to our customers and served to our customers. At this time, we had about 40 zones with forecasts, and we only trained the zone when the customer requested it. And in total, we had roughly 80 models into production. And for a while, that was quite enough and working well. But last year, we decided to set up a game, and we got actually very frustrated with our existing setup. For starters, our models were starting to be a bit like magic boxes. It was very hard to explain our model's features. Why would the consumption over the last 5 days affect the future carbon intensity? Why does the rainfall in the neighboring region increase the coal production elsewhere? It was very hard to understand all the signals that were coming in and how they were influencing everything. So it became very hard to debug our models when they were producing forecasts that we could not understand, because simply put, the problem was too big to tackle like this. Furthermore, validating our outputs was a complex task. Is a 60-gram carbon intensity for a given zone a legit output? Well, we have historical values that we can use to estimate if it's within a reasonable range, but we are kind of lacking the underlying explainability to understand how this value was computed and if it makes sense. For example, is this increase in power carbon intensity linked to a new power coal plant that has been added, or is it because they imported more their electricity from a more carbon intensive zone? And those answers we were not able to find them in our models. Another problem of forecast was built in a separate offering, as I said, and the results were stored in a different format and on a different infrastructure, which was kind of a hassle to maintain. Speaking of infrastructure, the first iteration was great to experiment, but lacked a lot of structure and flexibility that could allow to like switch a model or retrain new models regularly, because every time we had to run the notebook, so one of our data scientists was doing that. So that's why last year we started a journey to completely redesign our forecasting pipeline. We had two things in mind when designing it. The problem was too big, we need to break it down. And we already have great tooling actually that is working in the real-time pipeline. Let's just reuse that. So that's how we ended up deciding that we don't want to forecast the carbon intensity directly. We should forecast individual events first and then feed them to the normal pipeline like any other measured events, which will at some point in the pipeline give us the carbon intensity of the zone. That's how we ended up with, instead of 2 prediction engines, dozens of granular prediction engines per zone, one dedicated to forecast each kind of event that we already get from a parser. So consumption, exchange, solar production, hydro storage, battery storage, etc., etc. If we zoom in on one individual prediction engine, let's say the hydro production engine for this US zone, we end up with a very small and explainable model. We can see that it's being influenced by the temperature in the zone and the forecasted solar in a neighboring zone, as well as the hydro consumption in neighboring zones. It's way easier for us to improve our modeling of the signals because we can focus on a unique signal and then fine-tune it. And this leads to more explainable models that are way easier to use for us. We are then reconstructing the carbon intensity forecast later in the pipeline by computing the state of a zone through the same pipeline as the real-time data. This allows us to have all the same quality assurance tooling that we have in place already and have a better data operability across all of our systems. This leads us also to have a unique data offering for all of our customers, so they get always the same format everywhere, which is great for them. I showed you also a bit earlier that we scaled up our solution to have 10 times more models per zone than we used to. We also increased the number of served zones due to honestly popular requests from customers. So we had to undertake big structural changes to be able to maintain now more than 1,000 models in production. Or all the infrastructure with training set up in a notebook and shipping the models with code was no longer a viable option anymore. We greatly invested in our ML infrastructure to make it more robust, more flexible, and more scalable. And I'm going to take a little detour to like talk you a bit what we used in our prediction pipeline, because that's my day-to-day work right now. So to store and delivering models, we use a standard ML flow model registry, which was just great for us because we can then sort everything. Like we directly here see that, for example, this model here is the exchange model for Argentina and Chile. We see which version is being run. Right now, we are just running the latest version always in production, but later we're gonna have a more versioned approach. And we are able to click on the model and directly get a lot of information about our models. So it's make it all like so much easier this way. We can see the metrics when it was trained and evaluated. We can see the features that are being used directly. We can see also how it behaved during training and evaluation. This is way better for us to debug our models and just being able to understand what is happening under the hood. Why is a model drifting? And actually, speaking of which, now we have the possibility to train way more, we have the need to train way more models. And we couldn't do this in a notebook on an individual data scientist's computer anymore. We had to really set up a game here. And we used Google Cloud as data flow pipelines, but any pipeline could work here, but this one was really scalable for us to like compute all the features and being able to train all of our models at once or selected models. This enabled us to like train automatically all of our models. And also when a model is starting to drift, retrain it, because actually our models are very sensitive to some changes in data. And it happens quite a lot that one season doesn't resemble another one in electricity data. So there is a need to retrain your models almost every week, kind of. So now that we have a really easy way to do this with like our pipeline, this works way better. We use also the tracking features of MLflow to like analyze a bit more what the pipeline is doing when it's training models. For example, here it's easy to track down that, okay, this training model failed. Why is that? Actually, that's Sweden. And it's quite normal that the training for battery storage in Sweden would fail, because I know that in this zone in Sweden, there is no battery, actually. They don't need any battery in Sweden. So we were also able to make now 10 times more predictions by with a very simple setup, which are just like configuring Google Cloud Run jobs on the Google Cloud and like spreading all the predictions across multiple tasks, which allowed us to make way more predictions than before. And now to finish, let's talk about the juicy part about when can we schedule our workloads. So let's imagine something simple now. We have a batch job to process. How can I run it with the least carbon impact? There are two dimensions to these problems, the location and the time. I could choose a time where the lowest carbon intensity to run my my computation in a data center in Oregon is like, I don't know, around 9 p.m. But I could also choose to like switch location, and there might be a lower time that is better in California. So those two aspects are being taken into account and should be taken into account. However, you should also remember that there is a computational cost associated with moving your data around. So it might be better to stay in just one location unless your data is kind of already spread out in multi-regions cloud deployment or something like this. So maybe you're wondering, how do our customers what do they do with our forecasts? Well, actually, I might disappoint you here a bit, because, well, we don't exactly know. They give us insight about what they do and how they are doing things, and we are trying to help them understand the different signals so that they can minimize the carbon impact. But that's a bit where our knowledge stops, because the implementation is always up to them. For them, an API is ideal because they know better how to integrate our signal into their infrastructure. They also know better the constraints on the scheduling. Which data center can they use for location shifting? What constraints do they have? What priorities does a workload have? Finally, it's also way better for them to not allow us into their inner workings. Honestly, the less third parties in your system, the easier you can sell it to your information security department, and the faster you can like streamline the development pipeline. We do, however, participate in the Green Software Foundation to allow the SDK to use our data. And I think this community approach will at some point leverage some good things. The only thing is that we are right now not focusing on it, just focusing on the data and providing a reliable API so that customers can schedule their own workloads. But I'm not going to finish right here. I'm going to tell you a bit how we internally created our own carbon-aware scheduler. We, for ourselves, only optimize for time because our data so far is always stored in one region in Europe. So we didn't feel the need to optimize also for a regional location. But we just choose historically which region has the lowest carbon on an annual basis or on an hourly basis. So let's imagine we have this simple job that we have to run that needs to execute a Cloud Run function. We provided a deadline by which it should run and an estimated time. And we store this in a config. We have a scheduler that runs every hour that calls our API for the selected zones and should determine what is the best time to run then your computation. This, when it has determined this, it would like just take in the minimum that can also fit the estimated time provided. We create then an execution file. This is stored, and this creates a trigger that will trigger the job once the time has come. But this scheduler also reruns every hour because, well, the data changes quite a lot over time. The closer you get to the date, actually, the more accurate forecast you have, and then the carbon intensity changes every hour, kind of. Our prediction can change. So the scheduler might find a better time, and it then updates the trigger so that it runs always on the most optimal time. Finally, well, when the time comes, we just like execute the trigger starts the job, and then the output is stored so that it can be reused elsewhere. So that would be all. So thank you for listening. In a nutshell, to summarize a bit what we saw, there are good times and bad times to train your models or any intense computation for that purpose. So choose wisely. You can also choose the location, which is quite important on cloud providers nowadays. You can break down your problems into smaller sub-problems that will make your life way more easier during modeling. That's what we learned the hard way at some point, honestly. You should invest in ML infrastructure. You will definitely love it once it's in place. And you also can build your very own carbon-aware scheduler. So thank you. And I think we have some time to take some questions in the Q&A.
Yeah, I think you've answered the first question, Robin, but maybe the second one from Henry would be a good one to take. If you want to just read it off and then answer, that would be great.
I can do it. Have you looked into evaluating carbon intensity based on marginal carbon emissions, i.e. looking at what source would be dispatched to produce more electricity on demand at the relevant time? Because even if 80% of the grid is renewable at 2 p.m., if you add a load of X kilowatt hours, that would be met by methane gas being dispatched. Shouldn't you counter carbon intensity based on 100% methane rather than renewable, or than 80% renewables? That's a very good question, and maybe I'm not the best to answer here because some of the data analysts on our team have like way better answers than me. But we do also have like a marginal offering for this. The only thing is that so far we have found out that the average signal worked best for those kind of use cases in the long run. And the marginal signal was also rather suited more for like short gains in the long. So we have looked into it, and we are trying to offer both. So far, like this pipeline has been optimized for like the average one, but we are gonna roll out at some point later in a marginal one as well.
Wonderful. Thank you so much. And then Henry, maybe you can reach out to Robin separately as well to get a little bit more insight from the others in his company on this question. But with that, I want to go ahead and thank you, Robin, for your wonderful presentation. And thank you all for joining us today. This is the last presentation of the day.